In this video, we're going to talk about our second to last type of conic section, and that is the ellipse. So much like we did with circles and with parabolas, we're going to start with a very geometric definition, and you can see I'm setting up for a picture below, so we'll illustrate the definition informally in a picture. So here is the definition. I pre-wrote it so that I could just paste it in. An ellipse is the set of all points in the plane, the sum of whose distances from two fixed points, F1 and F2, is constant. So for our purposes, we're going to start looking at ellipses where these 2 points, they're called the foci. So F1 and F2 are called the foci, which is the plural of the word focus. We're going to look at examples for right now of foci that are symmetric about the origin, okay? So let's just say for the sake of argument that in this picture that I'm about to draw, the foci are roughly here and here, okay? So let's just say this is F1 and this is F2. Now, what I'm about to do is actually kind of fun to do with paper folds. It's easy to make an ellipse using a piece of string and a pencil and 2 pieces of tape. But I'm not going to go into that right now because I don't have that to show you. So let's just say that this point here, XY, is a point on the ellipse. So what we're saying is that if you take these 2 distances, the distance to F1, the distance to the distance to F1 and the distance to F2, and you add them up, so let's just say for the sake of argument, we'll call them D1 and D2, and whatever D1 plus D2 is, let's just call it some constant K. If I take any other point on the ellipse and I connect those 2 distances, I am once again going to have the same sum. So I'm going to roughly sketch in the ellipse. So again, I'm not doing precise measurements. I just want to sort of get the sense across. So let's sketch in the ellipse. Okay, so something like this. Many of you are going to look at the shape and you're going to say, oh, it's kind of like an oval. Okay, something like this. So this is an ellipse, and what I'm telling you here is that if you take any other point on the ellipse, say this one, and the 2 distances are different, but if you take the distance to the first focus plus the distance to the second focus, the sum of those two distances will be the same. And so, say, we look at a third point, same thing. That if you look at the distance to the 2 foci from that point, and you add them, that sum is always going to be the same. So if you remember with the circle and the parabola example, we actually derived the equation of the circle and of the parabola using the definition because it was pretty clean and pretty straightforward. There was just the one distance or the 2 distances that had to be equal. Here, because there are 2 distances being added together, it's still entirely possible to derive the equation of an ellipse using the distance formula, but it's kind of a lengthy and convoluted derivation, so I'm not going to do this in this video, but if you're interested in it, it's in your book, so you can also look it up there, but I'm happy to go over it with you in office hours. Instead, what I'm going to do is I'm going to go to the next page now that we've talked through the definition of an ellipse, and I'm going to list and sort of go over the two sorts of ellipses that we're going to talk about for now. So you'll notice that I have here two ellipses. One that's sort of longer horizontally than it is vertically. And so in this case, we say that the major axis of this ellipse is horizontal. Okay, so in other words, parallel to the x-axis. So the major axis is the longer one of the two, and in this instance, the major axis is horizontal. The minor axis, every ellipse has a major axis and a minor axis. The minor axis here is vertical. So if you look at the minor axis, that's this one here. Okay, so the minor axis is the shorter one of the two, and in this case, it's vertical. So because the major axis is horizontal, the way that we write the equation of this ellipse is x squared over a squared plus y squared over b squared is equal to 1, where a is greater than b, and of course a and b are both positive. Now, what are a and b? How do you find the focus, and so on? So I'm going to do a few labels here. And what I want to point out is, even though these aren't circles, so in a lot of ways it doesn't make sense to talk about a center, we will talk about the origin as sort of playing a central role, because everything here is symmetric about the origin. In particular, and again, this is true in the instance when everything is centered about the origin, the endpoints of the major axis are going to be A0 and negative A0. In other words, they are A units away from that central point in both directions. In the case of the minor axis, these 2 points are going to be 0b and 0 negative b. So you can see there that b is the length of sort of half of the minor axis, and a is the length of half of the major axis. So we generally assume that a is the larger of the two numbers. Now you might be thinking to yourself, wait a minute, but there was some mention about the focus. So what role does the focus play here? So the foci are these 2 points. So I'm putting down the ballpark location. So something like this. So let's call them F1 and F2. And just like everything else, the two foci are symmetric about the origin. So we will label them as C0 and negative C0. And here, C is equal to the square root of A squared minus B squared. Or you can also say C squared is A squared minus B squared. So those are the mechanics of an equation of an ellipse with a horizontal major axis. So now let's look here where we have a vertical major axis. So let me just write that here. Okay, so there is my major axis. So the major axis is vertical. And the minor axis is horizontal. Okay, so I think that if you kind of pause and think about it, this is going to make sense in terms of how we write the equation. So rather than writing x squared over a squared plus y squared over b squared, we're going to write x squared over b squared plus y squared over a squared is equal to 1. And again, and this is the part that I think is easier to remember, a is the larger number. So whichever variable has the larger denominator is the one that you are looking at as the major axis. I want to point out again that at this moment, everything we're looking at is symmetric about the origin. So while it doesn't make sense for an ellipse to have a center, it's not a circle, it does make sense to talk about it in terms of symmetry. Okay, so a lot like what we said with the horizontal major axis example, these 2 points are going to be 0a and 0 negative a, and these 2 points are going to be b0 and negative b0. So once again, I just want to stress that an ellipse does not have to have this beautiful symmetry about the origin. You could take your ellipse and you could shift it. However, nothing changes in terms of the geometry. So the minor axis is still going to be symmetric about that central point, and it'll still be the same number of units on either side, and the same is true of the major axis. So really hold on to that beautiful symmetry of the ellipse. Just like when the major axis was horizontal, the foci sat on the major axis, the same is going to be true here. The foci, once again, are going to sit on the major axis. And again, there's a little bit of symmetry, so we should be kind of mindful of that. Even if we're not plotting them super precisely, we should be mindful of that symmetric aspect. And again, the conventional notation for the foci is C. Okay, so we have 0C and 0 negative C, and those are our 2 foci. And just like in the example with the horizontal major axis, C is going to be the square root of a squared minus b squared. Okay? The last thing that I will say is that once in a while, you'll find yourself being given the length, say, of the major axis or the minor axis. So before we go on to the next piece about ellipses, the length of the major axis is always 2a, and the length of the minor axis is always 2b. So this is something you can very clearly see on the picture. So here is the length of the major axis, for example, and you can see because it goes from 0a to 0 negative a, the length there is 2 times a. And if we look at the minor axis here, you can see, even though it's vertical, it doesn't matter whether it's vertical or horizontal, but it starts at 0b and it goes all the way down to 0 negative b, so the length is 2b. So the reason that I showed that on the 2 examples is that it doesn't matter whether the horizontal axis is the major one or not. The lengths of the major and minor axis are always going to be 2 times a and 2 times b. So the last thing that I want to say is, and this may sort of answer a suspicion in your hearts, like, you know, an ellipse is kind of like a squished circle, isn't it? And in fact, this is true. So there is this relationship between a circle and an ellipse that tells you kind of how far off of being a circle is your ellipse. So what I have here in this last page is I have a picture of a circle, okay? And here we're going to spend just a little bit of time talking about the eccentricity. So when you have a circle, you have a single center. And one example that I like to give here is our eyes. So if you have perfect vision with no what's called astigmatism, what that means is that your eyeball is perfectly circular or perfectly spherical, and as light enters your eye, it all gets focused to a single point. Now, as we age, or perhaps just naturally, what can happen is our eyes can deform from being a perfect circle, and they can stretch out like so. And what ends up happening is that instead of having a single center, you now have two foci. So this is very extreme. It doesn't actually, like as far as your eye is concerned, it would actually be a very minor deviation, like maybe like so. And so now instead of having a single center, you might have two foci, right? So you might have foci that are very, very close to the center. So let me just erase this little guy. And maybe your foci are here, okay? Now, from the point of view of vision, what happens if you have an astigmatism, and of course the more severe your astigmatism, the more pronounced this is you have mild double vision. So it almost looks like you're seeing the same thing twice, but with like a small, with like a large overlap in the middle and small faint blurs on the outside. So the worse your astigmatism, the more pronounced this is. I like to tell this story because I have an astigmatism, and in fact, my astigmatisms are different in my two eyes, so it makes for a really exciting visit to the optometrist. But I remember the first time that I went to the optometrist, and she told me, you know, you have an astigmatism. And I had no idea what that was, and when she explained it to me, I said to her, I'm going to tell my class this every time I teach them ellipses from now on, because it's a purely mathematical phenomenon. Anyway, so the eccentricity is a ratio that measures essentially how far off circular the ellipse is. So I want to remind you, I'll put this here, that, and in this case, because we stretch the ellipse out horizontally, our major axis would be horizontal. Right? So the equation of this ellipse would be x squared over a squared plus y squared over b squared. And of course, you all remember from our previous page that c squared is this, c is the square root of a squared minus b squared. And I just want to sort of point out that for the purposes of our example here, like c is very small, right? This is a very, very slightly stretched out circle. So the two foci are very close to what would have been the center of the original circle before we stretched it out. So from the point of view of optometry, this is the most common situation. Very few of us have like football-shaped eyes, right? Kind of that oval football shape. Most of us, they're only a slight deviation from circular, and so the eccentricity is quite small. So what the eccentricity is it's the ratio, definition, the eccentricity E is the ratio of C to A. So if C is very, very small, like we see here, right? So here, the foci are very close to what was the center of the circle. Then you have a very small eccentricity, which means that it's an ellipse that looks an awful lot like a circle. It's just a little tiny bit off circular. As you have smooshed out long ellipses, more like the ones we had on the previous page, that's when you have larger eccentricities. So just to go back to our picture here, if I stretch this out, something like this, so now if I were to plot the foci, even if I were to do it very approximately, they would be more here, right? So something like maybe this. So maybe this would be F1, and maybe this would be F2. And so now you can see, like, this is your C now. And that's a significantly larger number. So the closer C gets to A, so the closer C and A are to one another, the larger the eccentricity and the more kind of smooshed your ellipse is. Now, of course, because C is always going to be less than A, the foci are always on the inside of the ellipse. That tells us that the eccentricity is always going to be less than 1, but greater than 0. So the eccentricity is a number between 0 and 1 that tells us essentially how smooshed of a circle is your ellipse. And the thing that I found fascinating from my visit to my optometrist's office is that when we're talking about correction for, people with astigmatism in their eyes, the number that's used to indicate what correction needs to be used for astigmatism is essentially the eccentricity of the eyeball. So it's not exactly the eccentricity because you have to correct it, and your eyeball is not a circle, it's a sphere. So it's a little bit more involved, but it's very, very, very closely based on that. So I found that really fascinating because it's an example that probably all of us have heard of. All of us have probably been to the optometrist. If not, we likely will. And many of us have an astigmatism. And that's all an astigmatism is. It's when your eye, over time or just naturally, ceases to be a sphere or a circle and kind of smooshes down to become an ellipse. And the more smooshed it is, the bigger your astigmatism and the more pronounced that double vision phenomenon. So this is the basics of an ellipse. As I've said in the previous videos, I will make a video of examples where we answer some questions, but this is the basics for now, and I'll see you next time.